As the battery gets closer to full, it's harder and harder to find a.
What we really wanted to achieve here is, like, well, why? You know, why make this really fast car? An electric car is the best car. Tesla's new condensed super battery comes with only a 15-minute charging time, with promises of faster charging, ultra-high energy density, and driving ranges approaching 1,000 kilometers. This battery doesn't just raise the bar, it hurls it into a different stratosphere. What makes this moment even more compelling is the timing. As Chinese giants like CATL and BYD dominate the EV battery space with scale and affordability, Musk steps forward not just to compete, but to transform. Let's dive straight in. Tesla's battery evolution began when the company was founded in 2003 by engineers Martin Eberhard and Mark Tarpenning. Later transformed under the leadership of Elon Musk, Tesla faced a hostile automotive landscape. At the time, electric vehicles were largely dismissed as impractical novelties, limited by sluggish performance, short range, and prohibitively expensive batteries. The global auto industry was entrenched in the internal combustion engine, and even early hybrids like the Toyota Prius were viewed with skepticism in some markets. But Tesla saw something else. The key to making EVs mainstream wasn't just in sleek car design, but in breaking through the limitations of battery technology. From the outset, Tesla focused heavily on batteries, treating them not as off-the-shelf components but as the very heart of its vehicles. The company's first production car, the Roadster, was built on the chassis of a Lotus Elise but packed with over 6,800 lithium-ion 18,650 cylindrical cells, the same type commonly used in laptops, manufactured by Panasonic. These 18650 cells were repurposed and repackaged by Tesla engineers into a novel battery pack configuration. This move was radical. No major automaker had used consumer-grade lithium-ion cells on such a scale in a road vehicle. Yet this allowed Tesla to bypass traditional battery suppliers and deliver the Roadster with a then unheard-of range of over 200 miles, around 320 kilometers, per charge, something no EV had achieved at the time. But Tesla wanted more. The EV manufacturer deepened its collaboration with Panasonic and laid plans for something unprecedented in the auto industry, a vertically integrated battery manufacturing facility. In 2014, Tesla announced the Jigger Factory near Sparks, Nevada. By the time its first phase opened in 2016, the facility was the world's largest building by footprint. The idea was not only to produce battery packs in-house but also to streamline the supply chain, cut down manufacturing costs per kilowatt-hour, and scale EV production to meet global demand. This move paid off. Tesla's second major cell innovation came with the Model 3, launched in 2017. Here, Tesla shifted from the older 18,650 cells to the more advanced 2,170 format, a cylindrical cell measuring 21 mm in diameter and 70 mm in length, developed jointly with Panasonic at the Jigger Factory. These 2170 cells were a technical leap forward, offering higher energy density, better thermal management, and improved longevity compared to the 18,650 batteries. They enabled Tesla to offer longer-range vehicles at more competitive prices, cementing the Model 3 as the best-selling EV globally in subsequent years. But the biggest leap in Tesla's battery roadmap came during its much-anticipated Battery Day on September 22, 2020. It was here that Elon Musk and Tesla SVP Drew Baglino unveiled the 4680 tabless cell, a revolutionary design that marked a sharp departure from previous formats. At 46 mm in diameter and 80 mm in length, the 4680 offered 5 times the energy, 6 times the power, and a 16% increase in range compared to the 2170. More importantly, its tabless design, eliminating the internal tabs connecting the electrodes, reduced resistance and allowed for faster charge and discharge cycles while simplifying manufacturing. Tesla also introduced structural battery packs, where the 4680 cells would become part of the vehicle's chassis itself, improving rigidity and reducing overall mass. The manufacturing improvements tied to the 4680 included Tesla's new dry electrode coating process, acquired through its 2019 purchase of Maxwell Technologies. This technique eliminated the need for wet solvents in electrode production, cutting both cost and environmental impact. Since 2021, limited volumes of the 4680 cells have been produced at Tesla's pilot line in Fremont, California, and later scaled to Jigger, Texas near Austin. These cells now power select versions of the Model Y and Cybertruck, but it was clear this was a transitional phase leading towards something even more ambitious. That ambition materialized in 2025 with the reveal of Tesla's condensed battery, the culmination of 2 decades of research, thousands of patents, and multiple manufacturing revolutions. Though details were tightly held prior to launch, the condensed battery represents a shift from lithium-ion to a new solid-state adjacent chemistry, incorporating silicon nanowire anodes and high-nickel cathodes. This leap has resulted in significantly higher volumetric and gravimetric energy density, estimated at over 450 Wh/kg compared to around 250 Wh/kg for the 2,170 cells. The result is a longer range, faster charging, and drastically lower thermal risk. What is Tesla's condensed battery? Tesla's condensed battery is the next leap in energy storage, designed to redefine the metrics of performance, efficiency, and safety in electric power systems. Officially revealed in 2025, the condensed battery is the culmination of over 15 years of Tesla's vertical integration in battery research, from cell architecture to raw material processing. Unlike traditional lithium-ion batteries, this system packs significantly more energy into a smaller footprint while also offering advancements in durability, charging speed, and environmental sustainability. At the heart of this new system is its unparalleled energy density. Tesla's condensed battery exceeds 450 Wh/kg, a notable increase from the 250 to 270 Wh/kg achieved in the 2,170 cells used in the Model 3 and Model Y, and the roughly 300 to 330 Wh/kg achieved by the newer 4,680 cells powering select versions of the Cybertruck and Model Y. The leap in energy density means that vehicles equipped with these batteries can achieve longer driving ranges, potentially over 800 kilometers or 500 miles per charge, without increasing the physical size or weight of the battery pack. This makes the battery ideal not just for automotive applications but also for drones, aircraft, and portable power systems where space and weight are critical. One of the most transformative elements in the condensed battery is the use of silicon nanowire anodes instead of traditional graphite. Silicon has long been considered a superior anode material due to its ability to store up to 10 times more lithium ions per gram than graphite. However, the major drawback had always been expansion. Silicon swells up to 300% during charge cycles, causing degradation and reducing battery lifespan. Tesla, building on research from acquired companies like Maxwell Technologies and collaborating with research teams in Texas and California, developed a nanostructured silicon architecture that mitigates this swelling. These ultra-thin nanowires allow lithium ions to flow more efficiently while maintaining structural integrity, leading to both higher capacity and better cycle life. Complementing the silicon anode is a solid-state electrolyte replacing the liquid electrolyte used in conventional lithium-ion cells. Solid-state electrolytes, typically made from ceramics, sulfides, or polymers, offer significant safety improvements. They are non-flammable and eliminate the risk of leakage, overheating, or explosion caused by dendrite formation or thermal runaway. Tesla's electrolyte blend is believed to be derived from lithium phosphorus oxynitride, LiPoN, with proprietary stabilizers enabling high ionic conductivity and stability across wide temperature ranges. The result is a battery that can withstand extreme thermal and mechanical stress, opening doors for aerospace and military applications. On the cathode side, Tesla has opted for a high-nickel, low-cobalt composition, a shift that began with the 2170 and 4680 cells but is now refined to new levels. Traditional NCA, a nickel-cobalt aluminum, cathodes typically contain 80% nickel, but the condensed battery's formulation pushes this to 88 to 90%, drastically reducing cobalt content, which is expensive, ethically controversial, and environmentally damaging to extract. This change not only improves energy density but also aligns with Tesla's broader supply chain goals, reducing reliance on cobalt mining in the Democratic Republic of the Congo and increasing use of North American and Australian nickel sources. What truly sets the condensed battery apart is its cross-sectoral versatility. While Tesla's EVs are the primary deployment target, the company has designed this battery to be modular and scalable. In 2024, Tesla's energy division began testing condensed battery modules in its Megapack systems at the Moss Landing energy storage facility in California. The results showed a 38% increase in power output and a 25% decrease in thermal management costs compared to traditional LFP-based packs. Elon Musk has also hinted at applications in Tesla's Optimus humanoid robots and SpaceX's Starship systems, where high-density energy is essential and space is at a premium. Another key factor in Tesla's condensed battery is the manufacturing ecosystem surrounding it. Tesla's battery materials refinery in Corpus Christi, Texas, which became operational in early 2024, supplies key inputs like battery-grade lithium and nickel. This facility supports Tesla's strategy of vertical integration, reducing dependence on external suppliers and minimizing geopolitical risks. In tandem, Nevada and JGA Texas are scaling up pilot lines dedicated to condensed battery production using Tesla's dry electrode coating and advanced thermal compression bonding, which reduces water usage and simplifies cell assembly. The unveiling of the condensed battery in 2025 marks a new era in energy systems, but Tesla has made clear that this is not the final form of EV innovation. With enhanced performance, recharge times under 15 minutes for a full charge, and dramatically lower fire risk, the condensed battery has the potential to accelerate the mass adoption of electric vehicles, autonomous systems, and distributed energy grids. Technological turning point. The unveiling of Tesla's condensed battery in 2025 marks a definitive technological turning point not only in the electric vehicle sector but across the entire energy storage landscape. Unlike prior advancements that chipped away incrementally at battery limitations, this innovation delivers substantial, measurable improvements in energy density, safety, charge time, and longevity. These gains are not theoretical or aspirational. They are now being implemented into early-phase production systems and are expected to scale through Tesla's Gigafactories, starting with JGA Nevada and Texas by late 2025. The implications are vast and quantifiable. Cars capable of driving 1,000 kilometers, or 620 miles, on a single charge, smartphones that operate for up to 5 days, and stationary batteries that can power entire off-grid communities or neighborhoods using renewables alone. The condensed battery achieves these milestones through a combination of technical refinements, silicon nanowire anodes that store nearly 10 times more lithium per gram than graphite, solid-state electrolytes that replace flammable liquids, and high-nickel, low-cobalt cathodes that reduce reliance on expensive, geopolitically sensitive rare earth elements. The result is a battery with up to 450 watt-hours per kilogram energy density, a major increase from the 270 watt-hours per kilogram provided by Tesla's 2170 cells or the 290 to 300 watt-hours per kilogram range for the 4684 watt. By integrating these condensed cells into a new platform architecture, tested on a Model S prototype and an experimental Powerwall X, Tesla effectively eliminates range anxiety, a long-standing barrier to widespread EV adoption. Consider the direct consumer implications. A mid-sized sedan equipped with a 100 kWh condensed battery pack can achieve over 1,000 kilometers of real-world range, verified during controlled track tests at the Ferment facility in April 2025. This is more than double the range of the average EV on roads today. Furthermore, this range does not come with a weight penalty. In fact, the condensed pack is 17% lighter and 23% smaller than its 4680 counterpart, enabling more flexible vehicle layouts and improved handling dynamics. For public transport, trucking, and electric aviation, such compact energy density opens the door to unprecedented use cases, including fully electric short-haul aircraft and heavy-duty trucks capable of cross-country freight routes without a single recharge stop. Moreover, the technology significantly reduces cost per kilowatt-hour by transitioning away from cobalt-heavy chemistries. Since cobalt has hovered around $33,000 per metric ton, and instead emphasizing high-nickel, silicon, and aluminum components, Tesla has slashed raw material costs by over 20%. Coupled with their vertical integration strategy and ongoing automation at gigafactories, the company expects a battery price of $55 to $60 per kilowatt-hour at scale by 2026. This is a crucial threshold. At $60 per kilowatt-hour, EVs become cost-competitive with internal combustion engine vehicles even without subsidies, making clean transport more accessible across income brackets and global markets, including countries in South Asia, Africa, and Latin America. The condensed battery also provides a viable foundation for electric aircraft, which had previously been constrained by the limited energy density of lithium-ion systems. In collaboration with SpaceX and a California-based aerospace partner, Tesla's energy division has initiated trials for lightweight modular battery packs for unmanned aerial vehicles and short-range passenger flights. These packs, tested at Edwards Air Force Base in early 2025, sustain up to 2 hours of continuous flight time on a single charge, double the previous record for electric-powered fixed-wing craft. But all is not well for Tesla. The biggest challenges Tesla faces are significant. Tesla's introduction of the condensed battery signals a seismic shift in energy storage, yet the path to full deployment is paved with formidable challenges rooted in engineering, geopolitics, economics, and public trust. The technology's advantages are real, but their realization at a global scale requires overcoming very specific and measurable hurdles. One of the most immediate obstacles lies in manufacturing complexity. The core innovations behind the condensed battery, silicon nanowire anodes and solid-state electrolytes, are not simply drop-in replacements for existing lithium-ion technology. Silicon nanowires, for example, must be grown in controlled environments using chemical vapor deposition systems that require submicron-level precision, similar to those used in semiconductor fabrication. This process is expensive, sensitive to contamination, and not easily scalable without clean room-grade environments. Solid-state electrolytes, meanwhile, must be deposited uniformly and without microfractures to ensure both conductivity and safety. Building production lines to handle these materials at the Jigger Factory scale, Tesla's benchmark since the Nevada facility opened in 2016, demands not only new equipment but also retrained labor, upgraded automation systems, and significant time. Even a minor imperfection in electrode layering or electrolyte application can lead to total cell failure. Scaling this from prototype batches to millions of cells per month at Jigger, Texas or Jigger, Berlin involves not just technical retooling but full system reintegration. Closely tied to production challenges is the issue of material availability. While Tesla has deliberately moved away from cobalt, long criticized for both cost and its link to unethical mining in the Democratic Republic of Congo, the demand for high-purity lithium, refined silicon, and nickel-rich cathodes has surged. Tesla sources lithium from the Silver Peak mine in Nevada and through deals with Australian firms like Piedmont Lithium, but global lithium prices have remained volatile, reaching $70,000 per metric ton at peak in late 2022 before stabilizing to around $20,000 per metric ton in 2024. Even at reduced cobalt levels, cathode production requires nickel of specific purity, which is not abundant and is geopolitically sensitive. The Philippines, Indonesia, and Russia are major players in nickel exports, and geopolitical instability or export restrictions could disrupt supply. Moreover, battery-grade silicon used in Tesla's nanowire anodes must be produced at 99.9999% purity, a process controlled by relatively few firms in the US, China, Japan, and Germany. In short, Tesla's material strategy must now evolve from price negotiation to geopolitical risk management, requiring vertical integration or long-term contracts with strategic reserves and mining operators. On the economic front, Tesla faces high initial costs associated with R&D, prototyping, and industrial scaling. The condensed battery is not a marginal evolution, it required billions in investment across multiple departments, including the Tesla Advanced Battery Research Facility in Canada co-run with Jeff Don's Dalhousie University Lab. Prototypes produced between 2023 and 2024 were estimated to cost over $130 per kilowatt-hour, double the industry target for cost-effective electric mobility. To hit mass-market viability, Tesla must reduce that to $60 per kilowatt-hour or lower, requiring exponential improvements in automation, yield rates, and manufacturing throughput. Elon Musk has hinted at 3D-printed electrode substrates, AI-managed factory lines, and modular manufacturing cells as part of the company's next-gen scaling strategy, but these are still in experimental phases. Every minute of factory downtime or rework caused by unstable process control at scale adds millions in losses. Regulatory hurdles compound the difficulty. Condensed batteries use materials and chemistry combinations that fall outside existing certification categories. Whether it's the U.S. National Highway Traffic Safety Administration or NHTSA, the Federal Aviation Administration or FAA, or the European Union's REACH standards, Tesla must secure approvals on dozens of parameters ranging from thermal runaway behavior to post-crash electrical stability. For example, the FAA is notoriously cautious about adopting new battery technologies in civil aviation following the Boeing 787 incidents with lithium-ion packs in 2013. Solid-state packs must demonstrate not just lab-tested safety but consistent real-world performance across wide temperature ranges, altitudes, and load conditions. Approval cycles can take 18 to 36 months per region, which could delay commercial applications in sectors like air mobility, grid storage, or even public transport. Lastly, Tesla must address consumer adoption barriers, which, though less technical, are equally vital. While Tesla enjoys brand loyalty among tech enthusiasts, mass-market EV adoption still lags. In 2024, EVs accounted for only 8.6% of global vehicle sales, with range anxiety, charging time, and cost cited as major deterrents. Tesla's past experience could be perceived as risk. Battery may well redefine what's possible. Public understanding of structural challenges are met with the ambition to reduce the breakthrough itself. Consumer confidence will hinge on problems not ending with validation, but on performance consistency across geography. In early 2025, a movement known as Tesla Takedown emerged, targeting Elon Musk's growing political influence and Tesla as a whole. A grassroots, non-violent campaign, it began in February 2025 and has since spread across the US, Canada, Europe, Australia, and New Zealand. The movement spans well over 250 cities, with coordinated demonstrations urging consumers to sell their Teslas, boycott purchases, and divest from Tesla stock to hit Musk's financial standing, both symbolic and practical. Fueled by Musk's high-profile role as head of the Trump administration's Department of Government Efficiency or DOGE, a civic restructuring office behind mass federal job cuts, the campaign views Tesla's brand as a proxy for Musk's political actions. Notable provocateurs like actor Alex Winter, sociologist Joan Donovan, and activist Valerie Costa have lent their voices, with some protests taking on a cultural tone, such as a dance against DOGE flash mobs outside dealerships in Washington, D.C. However, the movement hasn't been limited to peaceful picket lines. In Europe, including cities like Toulouse, Ottersberg, Rome, and others, multiple Tesla dealerships and supercharger stations have been burned or vandalized, sometimes coinciding with takedown events. Although the protesters maintain that they neither condone nor orchestrate such acts, law enforcement in France and Germany describes several of these incidents as potentially extremist. Tesla posted a 13% drop in global vehicle deliveries in the first quarter of 2025, delivering 336,681 units compared to 388,000 in the first quarter of 2024, which was already the lowest quarterly figure since 2022. European registrations fell sharply, 61% loss in the Netherlands, 64% loss in Sweden, and 37% loss in France, with Tesla's European market share contracting from 1.3% to just 0.7% by May 2025. In parallel, the stock has dropped nearly 30 to 35% year-to-date, erasing more than $150 billion in market valuation and pushing Tesla below the $1 trillion market cap threshold for the first time since late 2024.